Answer down, answer down, answer down, answer down, answer down, answer down, answer down. Am I original? Am I the only one? Am I sexual? Am I everything you need? You better rock your body now. Everybody.
Hey everybody, welcome to your video on particle motion. So particle motion is a pretty big deal in Unit 5 and also kind of Unit 4. We've been referencing particle motion a little bit throughout the year, and we did connect how position, velocity, and acceleration are related to one another, but we're going to go in a little more detail with this video and then practice a lot more questions to make sure you're good on the free responses and multiple choice. Just so you know, I usually call it particle motion, but this is also sometimes called straight line motion or rectilinear motion. So if you see those, they all mean the same thing. And as we've been saying, it's position or displacement, which we're going to talk about in just a minute. There's a difference. Velocity and speed, also there's a difference there, and acceleration. So those are the 5 main words we're going to be using here. One other thing to keep in mind, our particles that we're going to be talking about are going to be moving in a straight path, like left and right, or they could be going up and down. You can have things that move around like this. That would be more like a parametric motion where it's not really moving along a function. That's a little bit beyond the scope of the AP exam. So we're typically going to deal with left, right, for the most part, sometimes up and down. All right, my physics people, you probably have talked about this a lot, but I just want to say it one more time in case you haven't done physics or in case you did it last year and not this year. Displacement. All right, what is displacement? Displacement you want to think of as net change. So it's a net change of where you are after you've already moved. So let's say you start here and then you move 10 meters to the right. You stop and then you move 10 meters to the left. Your displacement is 0 because the net change from where you started to where you ended, there is no change. You're back where you started. So even though you've moved 20 meters, your displacement is going to be 0. That is different from total distance traveled. That's like the odometer in a car. Like if you get in your car and you drive to school and then you go back home, your displacement was 0 there, but your odometer racked up miles. So it's like the odometer in a car. So it's how far you move even if you end up in the same spot. So in this scenario here, your total distance traveled would be 20 if you go 10 to the right and 10 to the left. So very important that you don't mix these up because both of these are asked on the exam and we're going to practice answering both of those. All right, before I go to the next slide, make sure you have that jotted down for yourself. The next slide is just summarizing or organizing everything you need to know about position/displacement. Velocity / speed, and acceleration. So I would just make yourself 3 columns here. We're going to fill in some blanks here and then do a couple sketches. All right, so I finally looked up what this SFT business is because I remember in class I was saying I don't remember why it's SFT, and it seems there's not 100% agreement in the academic world about why SFT is used. Some people think it's derived from Latin, which I guess would make sense because Newton wrote his book Principia Mathematica in Latin. Most people wrote in Latin back when some of these discoveries were made. So there's a Latin word called, I don't know how you want to say that, spatium. So in Latin, that means space or distance. So that could be where it's from. That's what some people think. Space or distance. Some people think it's from the Latin phrase in situ, which means on site or in position. However, some people claim that S is for the German word Strecke, right here, and that means route or distance. I don't know. I kind of think it comes from the Latin prefix or Latin derivation, but just so you know, probably from the Latin, but there is a little bit disagreement. Either way, SFT was adopted in a lot of early physics textbooks, so most people recognize SFT as position, not speed, okay? So Anyway, position is scalar, so that means there is no direction here. It's going to be measured in feet, miles, meters, like some kind of distance here. And it's going to be your position on the x-axis or even in the air, depending on if you're like going up and down. So let me do a little sketch here and make sure you're good on reading a distance or position graph. Okay, so draw yourself a little grid up to 3 and draw something that looks remotely like this. And whoop. Remember, this graph is not the path of the particle. So we have a particle that's moving left and right. So you don't want to think like, oh, my particle is going up and then down and then up. This tells you where you are on the x-axis. Okay, so what this means here, if I were to refer to a number line, let's take like at 2 seconds. Pretend that's at 3. This means that if I'm on a number line here, 0, 1, 2, 3. At 2 seconds, I am at 3 on the number line. And then after 3 seconds have passed, I'm at like 1.5 on my number line. And then if that was 4, after 4 seconds, let's say that's -1, I'm back here on -1. So this tells you where you are at on the x-axis. We're moving left and right, not up and down. All right, what about velocity / speed? Let's talk about that one here. All right, velocity has magnitude and direction. So it's denoted with V of t. It's going to be feet per second or miles per hour. Those are the two most common ones, but really any kind of rate of change. So V of t, if you have velocity, we can say it is the derivative of position. So we wrote this down a while ago whenever we were doing higher order derivatives. But write that down one more time just so you have it to refer to. Now let's say I take velocity and then I do the absolute value of it. So absolute value will get rid of the direction. Remember, velocity does have direction. It tells you if you're going left and right. If you do the absolute value, there's no more direction. Now you have the magnitude of your velocity vector. That just tells you how big the velocity vector is. And it's going to give you speed, which is scalar. No direction, just magnitude. Okay. Let's think about this here. Velocity, we said, has direction. So if I'm moving this way at 50 miles per hour, that's different than if I move to the left at 50 miles per hour. If you move to the right, it's 50 miles per hour for velocity. If you move to the left, it's -50 miles per hour for your velocity. So velocity thinks these two things are different. However, speed can't really tell a difference between moving left and right. Either way, you're just going 50 miles per hour as your speed. So that is going to be the main difference there. All right, let's do another sketch here. Do something like this. All right, so here I have a velocity graph. And remember, if my velocity is positive, so up to like 5.5, so your velocity is positive, which implies you're moving to the right. And then here your velocity is negative, which implies we're moving to the left. And whenever you read this, what this means, this is something like, okay, after 2 seconds, my velocity is 3 feet per second. After 6 seconds, my velocity is -1 meter per second. That means you're going to the left 1 meter every second. All right. So there's your velocity graph, how you interpret those. Let's talk about an acceleration graph. We are going to revisit a velocity graph in just a minute here. All right, acceleration. What's the deal with that? Acceleration is a vector, just like velocity. So there's magnitude, which is like the number, and the direction. It tells you left, right, up, and down. We write A of t to represent it. The units here, feet per second squared, miles per hour squared. Physics people, you typically do meters per second squared. It tells you how fast the velocity is changing per time. So we'll practice interpreting a couple of those on the graph. A of t, if you want acceleration but you have velocity, just do the derivative of velocity. If you want acceleration but you have the position, just do the second derivative of position, and that will give you acceleration. All right, let's take a look at a graph here and make sure you're all set reading this one. I'm going to do something like this. All right, how do I read this? All of these, your acceleration is towards the right. So whatever force you have, acceleration you want to view as like a force. It's towards the right. I don't know what just happened there. Okay. And then here my acceleration is towards the left. And I have a couple visuals I'm going to show you on the next slide to refer to that. In order to read this, this means that at 2 seconds, or after 2 seconds have passed, at that 2-second mark, my acceleration is +1. So what does that mean for my acceleration to be +1? So listen carefully. For every 1 second, we increase our velocity by 1 meter per second. What about at 4? After 4 seconds have passed, at that 4th second, this graph is telling us for every 1 second, your velocity decreases by 3 meters per second. Now, one thing to keep in mind, if you're looking at an acceleration graph, you can't tell if you're speeding up or slowing down. So we're going to talk about speeding up and slowing down in just a second here. You also can't tell if you're moving towards the left or the right. You can tell if you're moving to the left or the right in these graphs, but not in the acceleration graph. So every graph tells you different information. The acceleration graph is a little limiting in those ways. All right, last slide here. Can you do a sketch here? I have a general graph, and then I have a more detailed graph. So here's your smaller, just quick general graph reminder. If you have a velocity here, anytime your velocity is above the x-axis, your velocity is positive, so you're moving to the right. If your velocity is positive, the object moves to the right. Even if your velocity is decreasing, like it's doing right here, the velocity is still positive, so you're moving to the right. At this moment here, the object has stopped, velocity is 0, and then here, your velocity is negative, so that means you're moving to the left, whether the velocity decreases or increases. As long as the velocity is below the x-axis, you're moving to the left because the velocity is negative. Speeding up and slowing down. We need to take a minute and talk about that. That's the last thing I want to talk about here with you all. How to tell if you're speeding up or slowing down. So I'm going to tell you 3 different ways, but then we're going to talk about, oh, why is this here? Then we're going to talk about how you can interpret it on the exam. So what you're looking at here is just a more detailed version of above. So please draw these arrows in because we're going to talk about like what on earth are these arrows here for. Speeding up and slowing down is always on the exam. It's a key concept for you to understand to be able to interpret whether you speed up or slow down. So let's talk about like what on earth are these arrows here because we haven't really drawn those ever this year on a graph. So this is a velocity graph. If you're given the velocity graph, you know a lot of information. You probably know the most information if you're given the velocity graph versus like the position or the acceleration graph. So these arrows here, the arrows are the magnitude of velocity. And what's the magnitude of velocity? Oh, the magnitude of velocity is speed. So that means these arrows represent the speed. Remember, speed doesn't care about direction, just the magnitude, like the number. Okay? So just with the arrows, we can tell if the velocity, or sorry, if the speed is increasing or decreasing, or if you're speeding up or slowing down. So like right here in this portion, your arrows are getting larger, which means your speed is increasing, which means you're speeding up. Here, your arrows are getting smaller, so the magnitudes are decreasing, which means you're speeding, well, you're slowing down. The speed is decreasing, so that would be slowing down. Here, your arrows are increasing. You're moving to the left now. The arrows are getting bigger, so you're moving left and going faster and faster and faster. So picture that. And then here you're still moving to the left, but you're moving slower and slower and slower because the magnitude of the velocity is decreasing. The arrows are getting smaller. And again here, you're not moving. So on the exam, you're not going to be able just to refer to like, oh, the arrows on the graph. You're going to need a little bit more than that. So let's talk about this in a different way here. Let's think about what I know based on my graph. If I only focus on this portion of the graph right here, on that portion of the graph, velocity itself is positive because Velocity is above the x-axis. What about acceleration? Acceleration is the derivative of velocity, so acceleration is the slope. All the slopes right here are positive. Even though the slopes are decreasing, the slopes are positive as well. So same sign, we were speeding up. Okay, what about the next section of the graph? Let's look here. Okay, velocity is definitely still positive, but if I look at my slopes now, the slopes are all negative. No matter what the slopes are doing, the slopes themselves are negative. The slope of velocity acceleration. So acceleration is negative, velocity is positive. Different signs there, we're slowing down. In this section of the graph here, I have velocity itself. What is velocity here? Okay, I'm below the x-axis, so velocity is negative. The slopes of velocity, which are acceleration, all these slopes are negative. So velocity and acceleration have the same sign, so we're speeding up. And on this portion of the graph, my last section, velocity is still, I should have matched my colors. Oh well. Velocity itself is negative. I'm below the x-axis. The slopes are all positive here. So acceleration is positive, velocity was negative. Opposite signs, we happen to be slowing down. So that's the big connection there. So on the exam, in order to justify if something is speeding up or slowing down, you're going to need to use this one. So I'm going to highlight this one and I'm going to put a star next to it. I would definitely, if you have a highlighter, highlight it or put stars next to it, circle it, something. This is how you're going to justify on the AP exam. AP exam justification. Nothing else is going to cut it for the exam, okay? They're very specific, College Board specific about how you justify this. So even though it's true, like yes, speed is increasing if you're speeding up. The magnitude of velocity is increasing, which is speed. The arrows are getting larger. That is all true, but you need to cite the signs of velocity and acceleration. Here, slowing down, yes, speed decreases, which means the arrows are getting smaller, but more importantly, velocity and acceleration have opposite sign. That's what the exam's looking for. To help you remember that, there's a couple scenarios you can think of. I'll go through a couple of these. All right, let's talk about, I kind of like the canoe with a river current. So let's say you're in a river, and here's my boat. Whoop. And let's say the current is moving to the right. So what you want to think about is acceleration is like the force acting on you. And velocity is more like your movement. Are you moving, are you moving left or right? So let's say my boat is moving to the right. So that means my velocity is positive. We'll say to the right is positive. And my current is also going to the right. So like if you're moving with the current, obviously you're going to speed up. And here, acceleration is positive, velocity is positive. If you ever find yourself in the unfortunate scenario where you are going against the current, so let's say you really need to go to the left. So that means your velocity would be negative, but the current is going to the right. So acceleration is more positive. Opposite signs, you're going to be slowing down no matter how hard you move your boat or how hard you row. The acceleration is going against you. Ultimately, you will slow down. Same idea if like you take a paper airplane and you throw it to the right, so the velocity is positive, but then you have this fan here. Whoa. And the fan is blowing to the left, so that would be like a force. The force of the fan is like your acceleration to the left. If you throw a fan and then if you throw an airplane and then you turn the fan on, the airplane's going to slow down and ultimately just drop. Whereas if the fan is going this way and then you threw the plane the other way, now my velocity is negative, my acceleration is negative, the plane's going with the fan. You get the idea. You're going to speed up. You can also think about if you're moving in the airport. If you're going this way, then, you can't even see that. Oh my God. Okay, if you're going this way, we can say like your velocity is positive and I don't even know what this thing is called. The moving tram, whatever. This carpet is moving to the right as well. That's like your acceleration. It'll speed up. I don't know if you've ever tried walking against these things. It's kind of scary, but you're going to slow down if you move against it. You can also think like walking up an escalator versus walking down an escalator. There's a lot of ways to picture this, but either way, you want to cite the signs of velocity and acceleration. All right, cool. So make sure you have that jotted down, and we will practice in class. See you later.